All right, welcome back. We are going to talk integral test for series. We are in section 11.3. So use the integral test to determine whether the series is convergent or divergent. Here we have n to the minus 6. Yeah, so we are going to convert this into an integral to use the integral test. You should probably note to yourself the fact that we are even able to do this is a function of the fact that between 1 and infinity, 1 over x to the 6th is continuous, positive, and decreasing. Those are the three criteria that must be satisfied for the integral test to even be applied. Definitely worth mentioning, boy, this great form when I see the integral test done and I see those things check-boxed on the paper. And similarly, those are great true-false questions where someone who is just blazing through the WebAssign might not even remember the assumptions to the integral test. And yeah, here's a moment to sort of talk about how WebAssign is sort of an imperfect system. That being said, because our function is positive, decreasing, and continuous on the interval 1 to infinity, we can just integrate x to the minus 6, which use the power rule here, play the improper integral out, and the improper integral and the series will have the exact same convergence behavior overall. It doesn't mean that they will converge to the same value. It just means they'll have the same overall behavior. So if one converges, the other converges. If one diverges, the other diverges. Right. Use the integral test to say if this series is convergent or divergent. Well, again, please note on the integral from 1 to infinity, you have a positive, continuous, decreasing function. Positive, because when n is 1 or greater, you get positive thing downstairs, positive or positive, positive. Decreasing as n gets bigger, the denominator gets bigger and the fraction gets smaller. And continuous, because the only point of discontinuity here would be at n equals 1/7, which is out of consideration. And so, since we are positive, decreasing, and continuous, we can apply the integral test. When you apply the integral test, use u equals 7x minus 1. Apply u substitution with an improper integral. Whatever the improper integral's behavior is, the behavior overall of the series will also be. But overall is the key word there. We're not saying that if the one converges to, if the integral converges to 12, the series converges to 12 too. No, we're just saying if the integral converges, so too does the series. If the integral diverges, as it does in this case, so too does the series. Here, we've got a classic u sub expression. Double check, note, this function, if you take that e as a power and put it downstairs, you will see that function is positive, decreasing, and continuous. Hence, the integral test can be applied. And if you apply the integral test here, u sub is going to be your friend. Let u equal minus x to the 7th, right? Because that's the thing that's inside the exponential function. And then the x to the 6th gets taken care of whenever you compute the derivative of u. This series is convergent. Well, it depends on the power of n, right? This is a classic p-test. So if you write this as 1 over sine to the 2, we just have to determine if sine to the 2 is bigger than 1 or less than or equal to 1. So use your unit circle, try to think this through. 2 is a weird number to put into a sine function, and yet here is an example where showing off your knowledge of trig can be very much on display. This question actually verbatim showed up on the final last semester, so full disclosure, there you go. Determine whether this series is convergent or divergent. Hey, check it out. This series has terms of the form 1 over x square root x, which means if you take x times square root x, that's what, x to the 3 halves. We got 1 over x to the 3 halves. That's a p-series because you got a power of your n in the denominator, and the question is, what is your power of n? Is it greater than 1? Is it less than or equal to 1? That's what you do with the p-test, and that's what's at play here. It doesn't apparently look like a p-test on the surface, but when you view it as n times square root n and take n and square root n and write that as n to the 3 halves, then it all comes together. Here's another p-series. 1 over n to the square root 2. Is square root 2 bigger than 1 or square root 2 less than or equal to 1? That's the question when it comes to a p-series. If you have 1 over n or anything where the terms are bigger, like 1 over square root n or something like this, well then, and 1 over n to the 1/2, well now you're going to diverge. But on the other hand, if you have 1 over n to something greater than 1, which this is like 1.4, 1 over n to the 1.4, you will converge, and that is what's going on here. Well, here we are as close to 1 as you could possibly be without being 1. Even if we were 1, we would diverge. And since this is not 1, we still diverge. So we're on the divergent side of things. That's just all there is to it. what is this? 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. So this is like 1 over n to the n, I believe. I mean, first off, this has to converge. But how do you deduce that? With the skills that we have, I'm a little bit perplexed. Oh, silly me. It's not n to the n. It's 2 cubed and 3 cubed and 4 cubed and 5 cubed. This is just 1 over n cubed. 1 over n cubed is a classic p-series. So here's another p-series. My gosh, beaten p-series over the head today. Okay, now let's step aside from p-series and let's deal with a classic integral test. This is an absolute classic, no doubt. And so if you notice, this function, because n is 2 to infinity, is going to be continuous, never 0 downstairs. You'd only be 0 downstairs at n equals 1 or n equals 0. It's going to be decreasing as n gets bigger, the denominator gets bigger. And it's going to be positive because ln n is positive when n is 2 or more, and n is positive when n is 2 or more. So we satisfy the integral test criteria. And if you try to integrate this, you can using u sub. Let u be ln x, and life is good. But double check your computation whenever you're going through it, because this one, you're going to have like an ln of something as that something gets big. And you're going to have to like take a moment and really process that to see why this integral diverges, and hence the series initially diverges. Right, consider the following, blah, blah, blah. What are the conclusions that can be made about the series and the integral test? Well, you see with the cosine pi x, sometimes that's going to be positive, sometimes that's going to be negative, which violates the integral test assumption. So we're not going to be able to use the integral test here because we are not positive on every term. Some of the terms are positive, some are negative, and that is too much variation for what the integral test allows. So here's a nice question. I probably would put this like one of the first questions to nail down the assumptions of the integral test before we start using it. Oh, that's the last question. So be it. There's a section of work on the integral test that felt kind of nice, and on to the next one.